In this example, we're asked to compute the work done by this vector field on a particle that's moving along this kind of straight line path. And the path is given by, so it moves from the origin along the x-axis to the point 1, 0. So the path is given by kind of 3 different line segments, it looks like. So this we'll call C1. And then it takes a turn and it heads back to the point, or up to the point 0, 1. So it goes up here. This is C2. And then after that, it goes back to the y-axis along, or sorry, back to the origin along the y-axis. So this is C3. And important here is that this point right here is 0, 1. So this is our path, and we want to find the work done by this force. Now, when we see this path encloses a very, very nice region. It's just a right triangular region in the plane. But the path itself is built out of 3 component paths, right? So 3 straight line, piecewise smooth paths. And to compute the path integral, we would have to break this up into 3 different path integrals. Now, I don't think that would be the hardest thing in the world, but let's try to use Green's theorem instead. So Green's theorem says that if our vector field, or our force field here, has components p and q, then the work done by the vector field, which is the path integral of f dot dr around this path, again that's where we would need 3 separate components, right? This is equal to the double integral over the region enclosed by the path. So this region in here, this is our region D. So it's the double integral over this region, but the integrand is the difference here, dq dx minus dp dy, integrated up with respect to area. Okay, so let's check this and see if this is going to make life easier, harder, whatever. So let's write this out. When I say write this out, multiply this first term out. So our p is going to be x squared plus xy. Our q is xy squared. That part is correct, right? It's fine. Here's our q. Here's our p. Let's work this out, right? So let's see what we get. What color did I use? Magenta for q. So dq dx, that's the x derivative of this component. That's just y. Sorry, y squared. That's y squared. Derivative with respect to x is y squared. All right. What about dp dy? Well, the dp dy, x squared does not have any y's. This is just xy, so dp dy is just x, right? It's just x. And so then to build our integrand, we subtract these. We get y squared minus x. So that's what we have to integrate up. Now, one of the advantages to doing this as a double integral is that now we can treat this region as either type 1 or type 2. Based on the integrand, I don't think it's going to matter. So let's just use type 1. That's usually the more standard way to go. It's what we're more familiar with. And if we're going to do this, then we need an equation for this bound right here, right? As a type 1, this has to be an equation y equals something in terms of x. And we see that this is a line segment that has slope -1, so negative x, and its y-intercept is positive 1. So this can be thought of as either 1 minus x or negative x plus 1. And we're going to integrate up then our y from 0 to this function, 1 minus x. Once that's been done, the x gets integrated from 0 to 1. Okay? And this is how we're going to compute the work. So let's do it. So, by Green's theorem, the work done by this vector field is the integral from 0 to 1 of the integral from 0 to 1 minus x of our integrand, y squared minus x, dy, then dx. This is an iterated integral, so we'll do the inside first. We're left with the outer integral still from 0 to 1. We integrate with respect to y here. So I'll put brackets still. This integral of y squared is 1/3 y cubed minus xy. And y is varying from 0 to 1 minus x. All right, we have to plug in these boundaries. So this is now integral from 0 to 1. This is now 1/3 1 minus x quantity cubed, right? Minus x times 1 minus x, and then minus a bunch of zeros. And this is what needs to be computed here. And we can just multiply this out. It's not the worst. So there are you could make some u subs here and make some changes, but I really don't think it's necessary because, like I said, we can just multiply it out. So we have 1/3 times, this when we multiply it out is going to give us 1 minus x squared minus 3x squared plus 3x minus x cubed. I wrote that in a very odd order, and it's actually the wrong order, right? So it's 1 minus 3x plus 3x squared minus x cubed. There, now it's right. I claimed that this was going to be easy to do, and then I messed it up. So then out here we have minus x plus x squared dx, and we can just combine like terms, right? So what's left here? From 0 to 1, our constant term, all we have is a 1/3. The next, our x term, we have minus 1/3 x, sorry, minus 1x minus another x, so minus 2x. Here we have plus a 1x squared plus x squared, so plus 2x squared, and then minus 1/3 x cubed. And then we go to the next term. So now we integrate, right? So this is going to be 1/3 x minus 1x squared after integrating plus 2/3 x cubed, okay, and then minus 1/12 x to the 4th, and we just plug in our boundaries, 0 and 1, so that means we just have to add up these fractions. So we have 1/3 minus 1 plus 2/3, that's 0, minus 1/12, and so this answer is minus 1/12. The work done by the vector field on the particle is minus 1/12.